Hey everyone, this is our first video on kinetics. I'm going to be talking about rates, rate constants, and reaction coordinate diagrams. The field of kinetics is concerned with measuring and analyzing reaction rates. Before we delve into specifics, I want to go through a thought experiment. Consider two reactions below. Reaction 1 has a starting material A converting to B, and reaction 2 has starting material C converting into D. I want you to assume that after some period of time, you can no longer detect any A or C starting materials in these reactions. I want you to consider two statements. Reaction 1 was over in 5 hours, and reaction 2 was over in 10 hours. And we're going to think about, is reaction 1 twice as fast as reaction 2? I would argue that with the information provided, it is too ambiguous to know for certain. We don't know the concentration of the starting materials starting out, or the temperatures at which the reactions were run. And also important is that we don't know how it was determined that the reaction was over, or when it was determined. I want to talk in more detail about what it means for a reaction to be over. And there are two ways that this could occur. A reaction could be over if the starting material is completely gone, or you could say a reaction is over if it reaches equilibrium. In this case, there is still some starting material left, and there's also some product, but the concentrations of those are no longer changing with time. I will argue that it's not actually possible for a reaction to be completely over in the sense of starting material being completely gone. What we're considering here is, in a general sense, a reaction of A to form B. Is it really possible for the concentration of A to reach 0? We could define an equilibrium constant for this reaction as being equal to the concentration of B over the concentration of A. Let's consider that we've reached the scenario where the starting material is completely gone. We would have the concentration of B divided by 0 for the concentration of A. This would imply that the equilibrium constant is infinite. Because delta G is equal to negative RT natural log of the equilibrium constant, if the equilibrium constant is infinity, then delta G is also infinite. This would imply that if the concentration of starting material reached 0, truly 0, then you would have an infinite energy difference between A and B. In reality, the difference in energy between the starting material and product needs to be finite, even if it's really large. And therefore, we can conclude that it is not possible for delta G or KEQ to be infinite, and the reaction can never truly end in the sense that the concentration of the starting material will never reach truly 0. It may become really, really small, but it will never be completely gone, even if you can't detect it anymore by standard methods. I next want to talk about reaction coordinate diagrams. The reaction coordinate itself is the minimum energy pathway for the reaction. We will typically draw this as a two-dimensional diagram known as a reaction coordinate diagram. You'll always have some form of energy on the y-axis. This could be Gibbs free energy or enthalpy. And then the x-axis is going to be what's known as your reaction coordinate. This doesn't have units, but it's essentially tracing the different molecules that you're passing through going along your reaction pathway. In this case, I'm showing a reaction with a single barrier where the product is lower in energy than the starting material. The transition state is going to be a high point along the lowest energy pathway. And here, because I'm drawing this two-dimensional diagram, I'm only showing the lowest energy pathway. You could have one transition state for a single step reaction, or multiple transition states for a multiple step reaction. In your reaction coordinate diagram, the intermediates are going to be low energy wells along the diagram. In this case, we could call the starting material and the product either those names, or we could call them both intermediates. Typically, I'll just use the word intermediate to refer to low energy wells that are neither the starting material nor the product. So, what is an intermediate versus a transition state? Organic chemists argue a lot about whether or not high-energy molecules are transition states or intermediates. It just depends on the shape of the energy curve. We're going to consider transition states as only having the lifetime of a single bond vibration. This timescale is 10 to the power of negative 13 seconds, an extremely short timescale. Anything that lasts longer than this is going to be an intermediate and a low energy well rather than a transition state. To draw transition state structures, we'll use dotted lines to show bonds that are breaking and forming. Let's consider an example acid-base reaction. I have ethoxide reacting with acetic acid. To predict the products, I would draw my two curved arrows for a proton transfer, using the lone pair of my base to form a new bond to the proton, and breaking the OH bond and bringing those electrons to oxygen. This proton transfer would form the neutral ethanol molecule and the acetate anion. Compared to my starting base, this acetate is stabilized by resonance, so I would predict that this reaction would be favorable. To draw the transition state structure, I would show the OH bond that's forming and the OH bond that's breaking as dotted lines, the oxygen of the ethoxide and the oxygen of the acetate that have negative charge in the starting material and the products each have partial negative charge at the transition state, and the proton that's moving between the two is going to have partial positive charge. This is because at the transition state, it no longer has a full bond. It rather has two partial bonds, which are weaker than a full bond. We could also consider an SN2 substitution reaction example using bromoethane and the nucleophile cyanide. Here as well, I would have two curved arrows. The carbon of the cyanide is more nucleophilic than the nitrogen, so it will attack the electrophilic carbon, and the carbon-bromine bond will break and the electrons will go with the bromine leaving group. At the transition state, I have a carbon with 3 bonds and 2 partial bonds. I have a dotted line between carbon and the leaving bromide, as well as a dotted line from carbon to the incoming cyanide nucleophile. The carbon of cyanide and the bromine that are leaving, that each have a full negative charge in either the starting material or the products, have a partial negative charge at the transition state. And the carbon, which doesn't have 4 full bonds around it at the transition state, is partially positively charged. We can identify the rate-determining step by looking at a reaction coordinate diagram. This step is important because it sets the observed rate for the overall reaction, determining how fast product is formed. The rate-determining step is decided based on what is the biggest barrier, looking from the reactant to the highest energy transition state. We'll consider 3 different scenarios here. The first example is a single-step reaction, which is our simplest scenario. If you only have one step, that step has to be the rate-determining step. Now let's consider a scenario where we have a two-step reaction. Here I have two transition states as well as an intermediate in between the reactants and products. In this example, the biggest overall barrier is going from the reactants to the intermediate. So this would be my rate-determining step. We could consider another two-step reaction where there's an intermediate here as well, but now my first barrier is smaller compared to my second one. In this case, the second step is the rate-determining one because it has the largest barrier between the reactant energy level and that of the highest energy transition state. I now want to talk about the relationship between a rate and rate constants. Here, let's consider a general reaction of starting material A going to form a product B. The rate of the overall reaction is going to be equal to K times the concentration of A. This lowercase curly k is my rate constant, and the A term is the concentration of the reactant, or reactants. Notice that the rate depends on the concentration of the starting material, and that starting material is going to disappear over time. This means that the reaction rate is going to change over time. Let's consider a plot of the concentration of starting material with respect to time. It won't always look like this, but it's pretty common for the concentration of starting material to decrease exponentially over time. The rate is determined by the change in concentration over time. This could be represented as negative of the derivative of the concentration of starting material over time. And we can determine this rate by looking at the slope of the line at different points along the reaction. At the start of the reaction, the tangent to my line is the highest. This represents a high rate. Midway through the reaction, this tangent is less sloped, corresponding to a medium rate. And toward the end of the reaction, this tangent, or slope, is pretty flat, corresponding to the lowest rate. So looking at the graph here, you can see that the rate is going to be highest at the beginning of the reaction, and it's approaching zero as the reaction proceeds. For each reactant, we can consider the order of the reaction with respect to that reagent. And certain reactants may or may not influence the reaction rate. Whether or not it does depends on the mechanism. And different reactants can have different influences on the rate, or rather, they can give rise to different reaction orders for different reactants. Really importantly, it's only the reactants that appear or are involved during or before the rate-determining step that will impact the overall rate. We'll call a reaction first order in a given reagent if the reaction rate linearly depends on the reagent's concentration. So doubling the concentration of the starting material should give you a doubled rate for a first order reaction. We'll call a reaction second order in a given reagent if the reaction rate quadruples as you double that reactant's concentration. And we'll call a reaction zero order in a given reagent if changing that reagent's concentration doesn't impact the reaction rate at all. So let's consider a 3-reactant system, A, B, and C, going to form a product P. As a potential scenario, I'm giving you an example where doubling the concentration of A doubles the rate, doubling the concentration of B quadruples the rate, and doubling the concentration of C has no effect on the rate. The rate law for this reaction would be that the rate would be equal to a rate constant K times the concentration of A times the concentration of B squared. We would describe this reaction as being first order in A, second order in B, and zero order in C. If you wanted to, you could put a C term in your rate law raised to the 0 power, but it's also okay to omit this. I want to briefly consider what is the fastest rate a reaction could have. This is going to depend on the number of molecules that are involved at the transition state. In the case where you have a unimolecular reaction with just one molecule involved in the transition state, the fastest this reaction could occur is the rate of a molecular vibration. This is pretty fast, and not all reactions will be this fast, it's just this is the maximum it could possibly be. This rate would be 10 to the power of 13 per second. In the case where you have two molecules involved in a transition state, this would be known as a bimolecular reaction. These reaction rates are going to be a bit smaller because the reagents need to diffuse to each other in order to react. Instead of being all set up and ready to react within a single molecule, you're limited by how fast your reactants can reach each other through either the solution or the gas phase. It works out, if you look at the diffusion through solution, this maximum could be about 10 to the power of 9 molar per second. This works out to being a smaller maximum rate compared to the one molecule system above. To end, I want to introduce a little bit more complexity into the idea of the reaction coordinate diagram and where it comes from. We're going to look at a multidimensional energy surface for what's known as a Claisen rearrangement. I'll show 3 potential mechanisms down below, but for now I want you to just look at these different starting materials, look at how the bonds are changing, and know that delta G is less than 0 for this reaction, meaning that it is favorable. The typical mechanism that's drawn is a concerted one, meaning all bond breaking and forming occurs in a single step. Your 3 curved arrows would be taking the carbon-carbon pi bond on the top to make a new bond to the lower right carbon, moving the pi bond on the bottom over a position, and taking the electrons from the carbon-oxygen single bond and using them to make a new pi bond. In this concerted mechanism, you have 3 different things occurring all at the same time. The carbon-carbon bond moves, a pi bond between 2 carbons moves, and you're forming a carbon-oxygen pi bond, all in the same step. Now let's consider another scenario. What if the carbon-carbon bond formed first, before the carbon-oxygen bond broke? Imagine taking the electrons from a pi bond and forming a new carbon-carbon single bond, and then taking a pi bond and making a new carbon lone pair in the first step. This would give you an intermediate where you have a new carbon-carbon single bond on the right. The top carbon has a positive charge, and the bottom carbon has a lone pair and a negative charge. Now imagine in a second step, we bring the lone pair from carbon down to form a pi bond, and take the electrons from the carbon-oxygen single bond and use them to form a pi bond. This is another way to get to the same final product as before. And let's consider a third scenario. What if the carbon-oxygen bond broke first? Here I'm taking those electrons and bringing them to oxygen because it's more electronegative than carbon. This would give me two different molecules. On the bottom, I would have a carbocation, and on the top, I would have an O-. Here I've drawn in the curved arrows to get from this intermediate to my product structure. I take an oxygen lone pair down to form a pi bond. I take two electrons from a carbon-carbon pi bond and use those to form a new single bond to the lower right carbon. And then I move the electrons from my other pi bond. Here again, I just have a different way of getting to the same product. What I'm going to show you on the next page, which as a warning is going to look pretty complicated, is a way of depicting all three of these possible mechanisms in a single multi-dimensional graph. I will call this my energy surface. And what we usually think of as a reaction coordinate diagram is just one slice of this energy surface. So, what's going on here? The yellow line is my starting material, and this other yellow line is my product. I'm considering a horizontal axis of CO bond breaking, and another axis coming out at you depicting the carbon-carbon bond formation. So let's consider our three cases. In the concerted mechanism, the case A from before, the carbon-oxygen bond is breaking and the carbon-carbon single bond is forming at the same time. I have a single transition state getting me from reactant to product. And notice that this single transition state I'm getting carbon-carbon bond formation and simultaneous carbon-oxygen bond cleavage occurring at the same time. Now let's consider our scenario B from before, where the carbon-carbon bond formed first. I'd first travel over a barrier, giving me carbon-carbon bond formation, and this doubly charged intermediate. I'm expecting this is relatively unstable due to its separated charges. Then I'd have a second reaction step with a barrier, giving me cleavage of my carbon-oxygen single bond and formation of the carbon-oxygen pi bond. And as a third scenario, let's look at case C, where we broke the carbon-oxygen bond first. I have one barrier getting me to a high energy intermediate corresponding to my two molecules that formed when the carbon-oxygen bond broke. I'm drawing this as higher in energy than the starting materials due to the fact that my two molecules are charged. From that intermediate, I would still have a second barrier corresponding to the carbon-carbon bond formation occurring in the second step. What we think of as our reaction coordinate diagram is just the lowest energy pathway. The molecule has all of the other options at its disposal, but it tends to react by the lowest energy pathway, in this case, the concerted blue one. Rather than drawing this complicated energy surface for every reaction, it's more practical to just draw the lowest energy pathway. For this example, a cope rearrangement reaction, I had a single transition state, or a concerted reaction, for this rearrangement event. I know that my product must be lower in energy than the starting material, because delta G was less than 0. Alright, so in summary, I wanted this video to introduce some of the topics of kinetics. We'll be delving in a lot more in future days. I talked about reaction coordinate diagrams, as well as transition state structures. I also talked about rates versus rate constants. how rate can change over time as concentration changes, as well as reaction order. That's it for this video. I will see you in class.